Right now, there is a region of space, 700 million light-years from Earth, that contains almost nothing. No stars, no planets, no galaxies visible to the naked eye. Just cold, empty space stretching for 330 million light-years in every direction. This region is called the Boötes void, and it is the largest known void in the observable universe. To understand why that matters, it helps to understand what we expected the universe to look like, and why the Boötes void contradicts that expectation so dramatically. When you look up at the night sky, the stars appear to be scattered fairly evenly in every direction. This was once the dominant assumption in cosmology, that matter in the universe was distributed more or less uniformly across large scales. But as observational astronomy advanced through the 20th century, a very different picture began to emerge. The universe is not uniform, it is structured. And that structure is far more intricate and far more dramatic than anyone initially expected. Beginning in the 1970s, astronomers started the ambitious project of building three-dimensional maps of the cosmos. Rather than simply photographing the sky, they began measuring the redshift of distant galaxies, the degree to which a galaxy's light is stretched toward the red end of the spectrum as it moves away from us. Because the universe is expanding, galaxies that are farther away move away from us faster, and so their redshift is proportionally greater. By measuring redshift, astronomers could estimate not just the direction of a galaxy, but its distance. For the first time, they could begin to plot where galaxies actually sit in three-dimensional space. What they found was astonishing. Galaxies are not scattered randomly. They cluster together into enormous filaments, thread-like structures hundreds of millions of light-years long, made up of galaxy clusters and superclusters, all gravitationally connected. Between these filaments are vast regions containing very little at all. These regions are called voids. The universe, it turns out, resembles a sponge, or more precisely, a foam. The matter is concentrated in thin walls and strands, and the spaces in between the bubbles and the foam are the voids. Cosmologists sometimes describe this as the cosmic web, a large-scale structure that spans the entire observable universe and organizes nearly all of its matter into these interconnected filaments and sheets. Gravity is the engine behind all of this. In the earliest moments after the Big Bang, the universe was hot, dense, and almost completely uniform, but not quite. There were tiny quantum fluctuations, microscopic variations in density from one region to another. These fluctuations were the seeds of everything that followed. In the regions where matter was ever so slightly denser, gravity was fractionally stronger. That stronger gravity attracted more matter. That additional matter increased the gravity further. Over hundreds of millions of years, and then billions of years, this process of gravitational amplification pulled matter progressively into the filaments and superclusters we see today. As the dense regions grew denser, the regions between them grew emptier. Matter drained out of the gaps and into the walls. This is the origin of cosmic voids. They are not random absences, but the logical consequence of gravity operating over billions of years on the large-scale structure of the universe. By most estimates, voids account for roughly 80% of the total volume of the observable universe. The universe is, by volume, mostly empty. The dazzling complexity of galaxies, stars, and planetary systems that we observe occupies only a small fraction of the total space. Against this backdrop, the Boötes void stands out even among voids. It was first identified in 1981 by astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman. While conducting a survey of galaxy redshifts in the direction of the Boötes constellation, they noticed something anomalous. A spherical region of space, approximately 330 million light-years across, that contained almost no galaxies. In a universe already known to have voids, this one was conspicuously, almost implausibly, large. To appreciate the scale, consider that our own Milky Way galaxy is roughly 100,000 light-years in diameter. The Boötes void is 3,300 times wider than that. If you place the Milky Way inside the Boötes void, it would be invisible against the surrounding emptiness, a single microscopic fleck in a volume so vast that light itself would take 330 million years to cross it from one side to the other. To travel from the edge of the void to its center at the speed of light would take 165 million years. In terms of distance, that is approximately 1.5 quadrillion kilometers, or roughly 1 quadrillion miles. And that is only the journey to the center. To cross the entire void from one side to the other at the speed of light would take 330 million years. The distance from Earth to the void itself adds another 700 million light years to any hypothetical journey. Our fastest spacecraft, built for robotic exploration of the inner solar system, travels at roughly 0.05% of the speed of light. At that speed, reaching the Boötes void would take more than 1 trillion years, roughly 70 times the current age of the universe. Human beings have not yet left their own solar system. The Voyager probes, launched in 1977, have traveled for nearly 50 years, and are only now at the very edge of interstellar space, still within the bubble of particles and magnetic fields generated by our Sun, and still only a fraction of a light year from Earth in cosmic terms. The nearest star to our Sun is Proxima Centauri, about 4.2 light years away. The Boötes void is 700 million light years away. The numbers are so disparate that direct comparison almost fails to convey the difference. Still, it is worth tracing what such a journey would involve, not because it is practical, but because doing so forces the mind to grapple seriously with cosmic distances and what they mean. Leaving Earth is only the beginning. The solar system is not simply a cluster of planets floating freely in space. It is a gravitationally bound system, and escaping it requires not just speed, but the right trajectory. A spacecraft leaving the Sun's gravitational influence must travel faster than the solar escape velocity, roughly 42 kilometers per second at Earth's orbital distance. Achieving this requires careful orbital maneuvering, typically using the gravitational pull of large planets to slingshot a spacecraft onto an escape trajectory. This is precisely how the Voyager probes and New Horizons were launched toward the outer solar system and beyond. Even after leaving the solar system, a spacecraft would still be deep within the Milky Way. Earth sits roughly 26,000 light-years from the galactic center, halfway between the center and the outer edge of the galactic disk. To reach intergalactic space, the region between galaxies, a spacecraft would need to travel another 26,000 light-years toward the edge of the Milky Way. At near light speed, that journey alone would take 26,000 years. Beyond the Milky Way, the character of the journey changes fundamentally. The density of stars drops off sharply. The sky, once filled with the faint glow of hundreds of billions of stars in the galactic disk, would become progressively emptier. Other galaxies would remain visible as fuzzy patches of light across the expanding darkness. Intergalactic space is not a complete vacuum. It contains tenuous gas, magnetic fields, and the faint afterglow of the cosmic microwave background radiation. But it is incomparably emptier than the interior of any galaxy. Continuing outward from the Milky Way, a spacecraft would pass through the local group of the collection of roughly 80 galaxies gravitationally bound together, dominated by the Milky Way and the Andromeda Galaxy, which lies 2.5 million light-years away. Beyond the local group lies the Virgo supercluster, of which the local group is a small peripheral member. Beyond that, the Laniakea supercluster, only identified in 2014, which spans 500 million light-years and contains the mass of 100 million billion suns. At some point along this journey, the density of galaxies would begin to thin noticeably. The filaments of the cosmic web would become fewer and farther apart. And eventually, ahead of the spacecraft, the sky would become darker. The fuzzy patches of light representing distant galaxies would disappear from the forward view. The spacecraft would be approaching the edge of the Boötes void. Entering the void would not be a sudden event. There is no wall, no barrier, no boundary that a spacecraft would cross in a discrete moment. The transition would be gradual, a slow fading of the cosmic background into deeper and deeper emptiness. Galaxy clusters would appear in the rear view, diminishing. The forward view would offer nothing but blackness. Inside the Boötes void, the experience of space would be unlike anything encountered elsewhere in the universe. The cosmic microwave background radiation, the faint thermal radiation left over from the Big Bang, permeating all of space, would still be present. The temperature of this radiation is approximately 2.7 degrees Kelvin, or negative 270 degrees Celsius. That is roughly negative 454 degrees Fahrenheit, just barely above absolute zero. In the absence of stars and galaxies, there would be no other significant sources of radiation. A spacecraft floating in the center of the Boötes void would be surrounded by darkness in every direction. No stars visible to the naked eye. No galaxies. The nearest galaxy would be tens of millions of light-years away, far too distant to appear as anything more than an imperceptibly faint smudge, even with a powerful telescope. In this environment, navigation would become profoundly difficult. Without visible reference points, a spacecraft and any crew aboard it would have no external frame of reference to determine orientation, position, or velocity relative to the surrounding universe. Instruments designed to track stars or distant radio sources could still function, but the intuitive human experience of space, the ability to glance at a star field and orient oneself, would be completely absent. This might seem like a minor practical concern, but it points to something philosophically interesting. Our entire framework for understanding our place in the universe depends on visible structure. We locate ourselves relative to stars, galaxies, and cosmic landmarks. In the Boite's void, nearly all of those landmarks vanish. It is the purest possible expression of the emptiness that characterizes the majority of the universe's volume. Despite its name, the Boite's void is not completely empty. This is an important nuance. Surveys conducted since its initial discovery have identified approximately 60 galaxies within the void. This is an extraordinarily sparse number. Given the volume involved, a normal region of the universe of equivalent size would be expected to contain thousands of galaxies. But 60 is not zero. These galaxies are not distributed randomly within the void. Most of them are grouped into a single filament, a thin strand of cosmic structure stretching through the interior of the void. This is itself revealing. Even within one of the emptiest regions of the known universe, gravity has managed to pull whatever small amount of matter was present into a structured filament. The cosmic web, it appears, extends even into the voids. It is simply far, far more tenuous there. The 60 galaxies of the Boite's void are thought to be outliers, the matter that happened to be located in the wrong place, when the surrounding regions were drained of their content by the gravitational pull of the great filaments and walls surrounding the void. They are stranded there, slowly moving, in a region of space where the density of matter is so low that the processes which build galaxies and star clusters have barely operated. Understanding exactly how the Boite's void formed, and why it is so much larger than the other voids identified in large-scale structure surveys, remains an open question in cosmology. One straightforward explanation is statistical. The universe contains an enormous number of voids, and in any large statistical sample, some examples will be extreme outliers by chance alone. The Boite's void might simply be the largest void that happened to form within the portion of the universe we can observe. On sufficiently large scales, the distribution of voids should follow predictable statistical patterns, and an extreme outlier like the Boite's void might be entirely consistent with the standard model of cosmology, just a rare occurrence that we happen to have detected. Some researchers, however, have explored whether the Boite's void might require additional explanation. Shortly after its discovery, astronomer Greg Aldering and colleagues argued that the void was too large to have formed through standard gravitational processes in the time available since the Big Bang. If the universe is 13.8 billion years old, there is a finite amount of time for gravity to have organized matter into the large-scale structures we observe. Some calculations suggested that a void of the Boite's void's size might be difficult to produce within this time frame. Subsequent work using more detailed simulations of cosmic structure formation has been more equivocal. Modern simulations of the large-scale structure of the universe, such as the Millennium simulation and its successors, can produce voids of substantial size, but generating something as large as the Boite's void remains at the edge of what standard models predict. Whether it falls within or outside the expected distribution depends on specific assumptions about cosmological parameters, including the density of dark matter, the density of dark energy, and the statistical properties of the initial quantum fluctuations from which all structure grew. Dark energy plays a particularly important role here. First conclusively identified in 1998 through observations of distant supernovae, dark energy is the name given to the mysterious component of the universe responsible for its accelerating expansion. As the universe expands at an accelerating rate, the distances between galaxy clusters increase over time. This accelerating expansion affects the growth of large-scale structure, including the formation and evolution of voids. In a universe with dark energy, voids expand faster than they would in a universe without it. As dark energy drives the surrounding filaments apart, voids grow larger over time. Some cosmologists have proposed that studying the size distribution of voids, including extreme cases like the Boite's void, could provide an independent way to measure the properties of dark energy and test models of cosmic expansion. This is not just theoretical. Large-scale structure surveys, currently underway, or recently completed, including the Dark Energy Spectroscopic Instrument, or DESI. The survey and the Euclid Space Telescope mission are mapping the three-dimensional distribution of galaxies across billions of light-years with unprecedented precision. These surveys are designed in part to study the cosmic web in detail, including the sizes, shapes, and distribution of voids. By comparing observed void statistics with theoretical predictions, cosmologists hope to constrain the properties of dark energy and refine their understanding of how the universe has evolved. The Botes void lies within the range of sky covered by some of these surveys. As the catalogs of galaxy positions grow more complete, the internal structure of the void, including the full population of galaxies within it, will become better characterized. Whether new galaxies will be found within it, and whether the void's boundaries can be more precisely defined, are questions that ongoing surveys may be able to address. The Botes void also connects to questions about the cosmic microwave background. The CMB, the thermal radiation left over from the epoch of recombination, approximately 380,000 years after the Big Bang, is one of the most precisely measured phenomena in all of physics. Its temperature is nearly uniform across the sky, varying by only about 1 part in 100,000 from one direction to another. These tiny variations encode information about the state of the early universe and are one of the primary data sets used to test cosmological models. Some theoretical work has explored whether large voids might produce a detectable imprint on the CMB through a phenomenon called the integrated Sachs-Wolf effect. As CMB photons travel through a large void, they gain energy as they enter the void because the void's gravitational potential is shallower than the surrounding regions, and then lose energy as they exit the other side. In a universe where dark energy is absent and the universe's expansion is slowing down, these two effects would cancel out perfectly. But in a universe with dark energy, where the expansion is accelerating, the void becomes slightly shallower over the time it takes a photon to cross it. The photon gains slightly more energy entering than it loses exiting, leaving a faint, warm imprint on the CMB. Detecting this effect for a single void as large as the Boytes void, at a distance of 700 million light-years, is an observational challenge. The signal would be tiny, comparable in magnitude to the natural statistical fluctuations in the CMB at those angular scales. But as CMB measurements have grown more precise and large-scale structure surveys have identified more voids, there has been increasing interest in stacking analyses, combining the CMB imprint of many voids to detect the average signal. This approach has shown promising results in recent years and represents another way in which voids are being used as cosmological probes. There is also an interesting connection between voids and dark matter. The standard cosmological model assumes that roughly 27% of the universe's total energy content is dark matter, matter that does not emit, absorb, or reflect light, but that exerts gravitational influence on normal matter. Dark matter is thought to play a central role in the formation of cosmic structure. Without it, the gravitational amplification of early density fluctuations would have been too slow to produce the galaxies and large-scale structures we observe today. In a void like the Boytes void, the density of both normal matter and dark matter is far below the cosmic average. Simulations suggest that the dark matter in void regions is present but extremely diffuse. Some researchers have proposed that studying the distribution of galaxies in voids, which should trace the distribution of dark matter even in these low-density regions, could provide new tests of dark matter models. Voids are, in a sense, the extreme low-density counterparts to galaxy clusters, which are the extreme high-density regions. Comparing the properties of structure at both extremes can help constrain cosmological models in ways that studying average density regions cannot. One more phenomenon worth discussing in connection with the Boytes void is the cold spot of the cosmic microwave background. The CMB cold spot is an anomalously cold region of the CMB sky, approximately 5 degrees across, located in the direction of the constellation Eridanus. In 2004, astronomers using data from the WMAP satellite identified this cold spot as statistically unusual, colder than expected given the standard cosmological model's predictions for CMB fluctuations. Various explanations have been proposed for the cold spot. One of the more intriguing is the existence of a supervoid, a vast region of very low galaxy density along the line of sight toward the cold spot. The reasoning is the integrated Sachs-Wolf effect described earlier. CMB photons passing through a large void in a dark energy-dominated universe would lose a net amount of energy, producing a cold imprint on the CMB. In 2015, a team of astronomers reported evidence for a supervoid in the direction of the CMB cold spot. identifying a region with a diameter of approximately 1.8 billion light-years and centered around 3 billion light-years from Earth. If real, and if confirmed, this would be even larger than the Boötes void, though at such a vast distance, surveying it completely is an observational challenge. The connection between the supervoid and the cold spot remains an active area of research, with some analyses supporting a causal link, and others concluding that the supervoid alone is insufficient to fully explain the temperature anomaly. The Boötes void itself does not appear to be related to the CMB cold spot. They are in different parts of the sky and at different distances. But the fact that astronomers are actively investigating supervoids as potential explanations for CMB anomalies illustrates how central the study of large-scale emptiness has become to modern observational cosmology. The question of what lies beyond the observable universe also connects, indirectly, to the study of voids. The observable universe, the region of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years. This is larger than the age of the universe distance of 13.8 billion light-years, because the universe has been expanding throughout the time the light was traveling. Beyond the observable horizon, the universe almost certainly continues, but we have no direct observational access to it. Within the observable universe, the largest structures identified span hundreds of millions to a few billion light-years. These include the Boötes void, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, and the Shapley Supercluster. The existence of such large structures is itself a subject of ongoing discussion. Some cosmologists have raised questions about whether structures larger than a few hundred million light-years are consistent with the cosmological principle, the assumption that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks the same in all directions and from all locations. If the universe is truly homogeneous on large scales, then the number and size of extreme structures, like the Boötes void, should be statistically predictable. Current observations are broadly consistent with this expectation, but the exact boundary at which the universe transitions to homogeneity, and whether all observed structures respect that boundary, remains a topic of active research. The Boötes void, discovered by a small team of astronomers using the relatively modest observational technology of the early 1980s, turned out to be one of the most scientifically consequential features ever found in the large-scale structure of the universe. At the time of its discovery, its existence seemed almost paradoxically difficult to explain. The universe was only a few billion years old. There had not been enough time, some researchers thought, for gravity to have cleared such a large region so completely. Over the subsequent decades, as simulations grew more powerful and observations more precise, the picture has become clearer, if not completely resolved. The universe's large-scale structure emerges naturally from gravitational amplification of quantum fluctuations in the early universe. Voids are an expected consequence of this process. The Boötes void is large, but not necessarily so large that it cannot be accommodated within the standard model of cosmology. What the Boötes void has done, more than anything, is force astronomers to take seriously the scale and character of cosmic emptiness. For much of the history of astronomy, the focus was naturally on what was visible: stars, nebulae, galaxies. The voids between them were understood to exist, but were not the primary subject of study. The discovery of the Boötes void, followed by decades of large-scale structure surveys revealing an intricate cosmic web dominated by voids in volume, permanently changed that perspective. Today, the study of cosmic voids is a recognized subfield of observational and theoretical cosmology. Voids are used as probes of dark energy through their effect on CMB photons. They are used to test modified theories of gravity, which predict different void profiles than general relativity does. They are used to study the properties of galaxies in extreme low-density environments, because galaxies in voids evolve differently than galaxies in filaments and clusters, subject to different merger rates, gas accretion histories, and tidal forces. Galaxies within voids tend to be somewhat different from their counterparts in denser environments. They are more often isolated, with fewer neighbors. They tend to be slightly bluer and more actively star-forming, likely because they have experienced fewer the galaxy-galaxy interactions and cluster environmental effects that can quench star formation. Studying these void galaxies helps disentangle the effects of internal galaxy physics from the effects of environment, a central challenge in understanding how galaxies form and evolve. The roughly 60 galaxies identified within the Boötes void itself are of particular interest for this reason. They exist in one of the lowest density environments in the observable universe, having evolved in near-complete isolation from the gravitational influence of other galaxy clusters or filaments. Whatever they look like today, whatever their star formation rates, their gas content, their morphologies, reflects a combination of their initial conditions and their evolution in a uniquely extreme environment. Future surveys, including those conducted with the James Webb Space Telescope, the Rubin Observatory, and the Square Kilometer Array Radio Telescope, will provide much more detailed information about galaxies in and around voids. The James Webb Space Telescope, with its unprecedented sensitivity in the infrared, can study galaxies at very high redshifts, that is, very great distances, and characterize their stellar populations and star formation histories in ways that were not previously possible. Although the Botez void lies at a distance where individual galaxy observations require substantial telescope time, the broader population of void galaxies across the universe will be studied in unprecedented detail. The Rubin Observatory, currently being commissioned in Chile, will conduct the Legacy Survey of Space and Time, a 10-year photometric survey covering roughly half the sky down to very faint magnitudes. This survey will identify enormous numbers of galaxies and will produce three-dimensional maps of large-scale structure more detailed than any previously available. The void population across the observable universe, including extreme voids like Boötes, will be characterized with statistical power that current surveys cannot match. The Square Kilometer Array, an international radio telescope project that will combine receivers across thousands of kilometers in South Africa and Australia, will survey neutral hydrogen gas in galaxies across large fractions of the sky. Since neutral hydrogen is a tracer of gas available for star formation, this survey will map the star-forming potential of galaxies in all environments, including voids. Understanding how galaxies in void environments have accumulated and retained their gas, compared to galaxies in filaments and clusters, will be a major advance in galaxy evolution science. All of this future observational work connects back to the fundamental question raised by the Botez void and by the existence of cosmic voids in general. How did the universe come to be structured the way it is? And what does that structure tell us about the physics governing the cosmos on the largest scales? The answer to that question involves understanding the initial conditions set by the Big Bang, the physics of inflation, the period of exponential expansion thought to have occurred in the universe's first fraction of a second, the gravitational dynamics of dark matter and normal matter over billions of years, and the accelerating influence of dark energy on the universe's expansion. Voids are sensitive to all of these factors. Their sizes, shapes, and distribution encode information about the universe's content and history in ways that complement the information encoded in galaxy clusters, in the CMB, and in the distribution of galaxies themselves. This is why cosmologists increasingly regard voids not as featureless absences, but as scientifically valuable structures in their own right. The Botez void sits in the direction of the constellation Botez, which is visible from the northern hemisphere in the spring and summer sky. When you look toward the area between the Big Dipper and the bright orange star Arcturus, which is the fourth brightest star in the night sky, you are looking in the direction of the void. The light entering your eyes from that direction has been traveling for hundreds of millions of years. Some of it passed through the Botez void on its way to you. That void, 330 million light-years across, containing almost nothing, is there, right now, in the direction you are looking. There are no stars there, no galaxies in any observable sense, no planets, just the faint thermal hum of the cosmic microwave background and the extraordinarily sparse matter of one of the universe's deepest silences. The Botez void was first noticed by human beings less than 50 years ago. In cosmic terms, that is an eye blink. And even in that short time, it has moved from an astronomical curiosity to a cosmological tool, a window into the nature of dark energy, the dynamics of structure formation, and the history of the universe itself. The questions it has raised are not yet fully answered. Whether it can be fully explained by standard cosmology, or whether it hints at physics beyond the standard model, remains to be determined. Whether the galaxies within it will yield new insights into galaxy evolution in extreme environments depends on future observations not yet made. What is clear is that the universe is mostly empty. The galaxies, stars, and planets that seem to fill the sky from our vantage point on Earth represent only a thin, filamentary scaffolding stretched across a vast structure whose dominant feature by volume is absence. The Botez void is the largest known expression of that absence, and understanding it fully is one of the ongoing challenges of modern cosmology. To appreciate fully what the Botez void represents, it is worth taking a step back and considering the history of cosmology, how our understanding of the universe's structure evolved from a static, star-centered picture to the dynamic, foamy, large-scale structure we recognize today. For most of human history, the universe meant the visible sky. The stars, the moon, the sun, the planets, these constituted the known cosmos. Even after Copernicus and Galileo established that Earth orbits the sun rather than the reverse, and even after Newton showed that gravity governs the motions of planets and moons with mathematical precision, the universe was still conceived of as essentially a single system, our solar system, surrounded by a fixed backdrop of stars at roughly uniform distances. The idea that the faint nebulae, visible through early telescopes, might themselves be island universes and distant systems of stars, comparable in scale to the Milky Way, was debated for over a century before it was settled. The so-called Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis crystallized the dispute. Shapley argued that the Milky Way was the entirety of the universe, and the fuzzy nebulae were structures within it. Curtis argued that the nebulae were external galaxies. The debate was resolved within a few years when Edwin Hubble used Cepheid variable stars, stars whose intrinsic luminosity is related to their pulsation period in a predictable way to measure the distance to the Andromeda Nebula, and showed that it was far too distant to be part of the Milky Way. It was an independent galaxy. This discovery did not just expand the universe, it shattered the previous conception of it entirely. The universe was not a single galaxy, but a cosmos populated by billions of galaxies, each containing billions of stars. And then Hubble did something even more consequential. He showed that the distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. This relationship, now known as Hubble's law, was the first direct observational evidence for the expansion of the universe. If galaxies are moving apart from us now, running that expansion backward in time leads to a state in which all the matter in the universe was compressed into an extremely hot, dense region, the Big Bang. The Big Bang theory, developed through the middle decades of the 20th century, provided a framework for understanding the origin and evolution of the universe. It predicted the existence of the cosmic microwave background radiation, the thermal afterglow of the hot early universe, which should permeate all of space at a nearly uniform temperature. This prediction was dramatically confirmed in 1964, when Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, detected an anomalous microwave signal coming uniformly from all directions in the sky. They had discovered the CMB, and the observation cemented the Big Bang as the dominant cosmological model. But the Big Bang theory, as initially formulated, left certain important questions unanswered. Why is the universe so uniform? The CMB is nearly identical in temperature from opposite sides of the sky regions that could not have been in causal contact with each other given the finite speed of light. Why is the universe so geometrically flat, meaning that the curvature of space is so close to zero? And why does the universe contain the specific pattern of small fluctuations in the CMB that we observe? The answer to these questions came with the development of inflationary cosmology proposed by Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, Andreas Albrecht, and others in the years that followed. Inflation proposes that in the universe's first tiny fraction of a second specifically, somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds, after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26th in an extraordinarily brief time. This exponential expansion would take a tiny, initially causally connected region and stretch it to a size far larger than our observable universe. The uniformity of the CMB is explained because the entire observable universe was once a tiny region in causal contact. The flatness is explained because the exponential expansion stretched away any initial curvature, just as the surface of a balloon appears flat when inflated to an enormous size. And the small fluctuations in the CMB that seeded all of cosmic structure are explained as quantum fluctuations, inherent uncertainties in the density of matter at the quantum level that were stretched to macroscopic scales by inflation. These quantum fluctuations are the ultimate seeds of the Botez void, the slightly over-dense regions that gravity amplified into the filaments and superclusters of the cosmic web, originated as quantum uncertainties in the density of matter during the inflationary epoch. The slightly underdense regions, the seeds of voids, equally originated there. The Botez void, in the most fundamental sense, traces back to a quantum fluctuation in the first fraction of a second of the universe's existence. The specific character of the inflationary quantum fluctuations, their amplitude, their spectral index, their statistical distribution is reflected in the pattern of structure we observe today, including the distribution of voids. One of the predictions of inflation is that the initial density fluctuations should follow a nearly scale-invariant spectrum, meaning that fluctuations occur with roughly equal power on all scales. This prediction has been confirmed by measurements of the CMB power spectrum, and it is consistent with the large-scale structure observed in galaxy surveys. Whether the specific size of the Bode's void is exactly what the inflation plus gravity model predicts, or whether it represents a statistical anomaly, is a question that requires careful modeling and comparison with large simulation ensembles. The most recent state-of-the-art N-body simulations, which model the gravitational evolution of hundreds of millions to billions of particles representing dark matter in a cubic volume of universe, produce voids of many sizes, including some very large ones. The question is whether the Bode's void size is within the range that the simulations produce with a plausible probability, given the volume of the observable universe. This kind of statistical reasoning, comparing observed structures to the distribution predicted by simulations, is central to modern cosmology. It requires large simulation volumes, because rare extreme events only appear in simulations that are large enough to contain them. It also requires careful accounting for observational selection effects. The fact that we are more likely to discover a large void if it lies in a region of sky that has been surveyed in detail. The Bode's void was discovered because astronomers happened to be conducting a detailed redshift survey in the direction of Bode's in the late 1970s and early 1980s. If that survey had been pointed elsewhere, the void might have remained uncharacterized for years or decades longer. The history of its discovery is a reminder that our knowledge of large-scale structure is strongly shaped by which parts of the sky have been surveyed and how deeply. Modern surveys like the Sloan Digital Sky Survey, which began operations in 2000 and has now covered a substantial fraction of the northern sky to great depth, have allowed a much more systematic census of large-scale structures, including voids. The Sloan Digital Sky Survey has identified tens of thousands of voids of various sizes. The Bode's void remains among the most extreme, but it is now understood as part of a broader population of cosmic voids, rather than a unique and inexplicable anomaly. It is also worth discussing what happens to galaxies over time in a void environment, because this is where the Bode's void's roughly 60 resident galaxies offer a unique scientific window. Galaxy formation is not a simple process. It involves the gravitational collapse of gas and dark matter, the formation of stars from molecular clouds, the feedback from those stars through radiation, stellar winds, and supernova explosions on the surrounding gas, the growth of supermassive black holes at galaxy centers, and their energetic feedback on the host galaxy, and the effects of mergers and interactions with neighboring galaxies. All of these processes are deeply intertwined, and disentangling the role of each one is a central challenge in the field of galaxy formation and evolution. One powerful way to isolate the effects of environment is to compare galaxies in very different environments. Galaxies in the dense cores of massive galaxy clusters experience strong tidal forces, ram pressure stripping of their gas by the hot intracluster medium, and high rates of galaxy-galaxy encounters. These processes tend to quench star formation, transforming late-type spiral galaxies into early-type elliptical or lenticular galaxies. Galaxies in void environments, by contrast, experience almost none of these effects. They evolve in relative isolation, subject primarily to their own internal physics. Studies of void galaxies from large surveys have found that, compared to galaxies in average density environments, void galaxies tend to be bluer, indicating younger or more active stellar populations, and to have higher specific star formation rates. They also tend to be somewhat smaller and to have slightly later morphological types, consistent with less environmental processing. These differences are not enormous. The internal physics of galaxies dominates their evolution in most respects, but they are statistically robust and provide important constraints on models of galaxy formation. The 60 galaxies in the Bode's void represent the extreme end of this continuum. They have been evolving in one of the most isolated environments in the observable universe, far from the influence of any galaxy cluster or major filament. Detailed studies of their properties, their stellar masses, their star formation rates, their gas content, their metallicities, their morphologies would provide an unusually clean test of galaxy evolution models in the absence of environmental effects. Of course, Studying individual galaxies at the distance of the Boyte's void, 700 million light-years, is observationally demanding. At that distance, even a galaxy the size of the Milky Way subtends a very small angle on the sky and is relatively faint. The current generation of large telescopes, including the Hubble Space Telescope and ground-based 8 to 10 meter telescopes, can obtain spectra of the brighter void galaxies, but detailed, spatially resolved studies showing the distribution of stars and gas within individual galaxies are difficult. The James Webb Space Telescope, with its larger collecting area and infrared sensitivity, will improve this situation, as will the upcoming generation of extremely large telescopes with primary mirrors of 30 meters or more. Thinking about the Boyte's void in the context of what the universe will look like in the far future is also illuminating. The universe's expansion is accelerating, driven by dark energy. If this acceleration continues indefinitely, which current observations suggest, then the distances between galaxy clusters will continue to grow over time. Galaxies that are not gravitationally bound to each other will drift progressively farther apart. On timescales of tens of billions to hundreds of billions of years, the accelerating expansion will push the currently visible universe beyond our observable horizon. The Milky Way and its gravitationally bound companions in the local group will remain together, but the rest of the universe will recede beyond the cosmological horizon, the distance beyond which the recession velocity exceeds the speed of light, making communication and observation impossible in principle. In this far future, the observable universe will consist only of the local group, a gravitationally bound island in an otherwise dark and empty cosmos. The great filaments and superclusters visible today will have dissolved into the expanding darkness. The voids, including the Boyte's void, will have grown even larger. The cosmic web, as a visible structure, will have largely disappeared from view. This is the long-term fate of the large-scale structure of the universe. Continued expansion, thinning of the cosmic web, growing isolation of gravitationally bound structures, and a universe that becomes progressively emptier and darker at the observable scale. The Boyte's void, already one of the emptiest regions in the present universe, foreshadows the eventual character of the entire observable universe on cosmological timescales. This perspective also throws into relief how remarkable it is that we exist at the present moment in cosmic history. The universe today is in a kind of middle age, when large-scale structure is well developed but still observable. The CMB is still detectable, distant galaxies are still visible, the cosmic web is still intact. A civilization that arose much later in the universe's history, in say 100 billion years, would find themselves in an impoverished cosmos, cut off observationally from the richness of structure that exists today. They would have no way to discover that other galaxies even existed, and no way to deduce the Big Bang or the inflationary epoch that preceded it. The evidence would have been swept beyond the cosmological horizon. The physicist and cosmologist Lawrence Krauss and astronomer Robert Scherer made this point explicitly in a paper titled The Return of a Static Universe and the End of Cosmology, published in 2007. They argued that future civilizations, emerging in a universe dominated by dark energy, would lack the observational evidence to discover modern cosmology. They would look out at a featureless, static-seeming cosmos and have no way to infer its true nature. From that perspective, the fact that we exist now, with the full richness of the observable universe available to us, including structures like the Boyte's void that encode the history of cosmic evolution, is a kind of cosmic fortune. The detection of the Boyte's void was also a pivotal moment in the history of cosmological observation because it helped motivate the massive investment in large-scale structure surveys that has characterized astrophysics over the past several decades. Before the discovery of the void and other large-scale structures in the early 1980s, the field of large-scale structure was primarily theoretical. After the discovery, it became clear that purely theoretical models needed to be confronted with data on the actual distribution of galaxies in 3 dimensions, at scales of hundreds of millions of light-years and beyond. This drove the development of the Center for Astrophysics Redshift Surveys, the Las Campanas Redshift Survey, the 2-degree Field Galaxy Redshift Survey, the Sloan Digital Sky Survey, and ultimately, the current generation of dark energy surveys. Each of these surveys pushed the frontier outward deeper in redshift, covering larger areas of sky, measuring more galaxies with greater precision. The cumulative result is a 3-dimensional map of the universe that covers substantial fractions of the observable volume and has revealed the cosmic web in extraordinary detail. Thousands of voids have been identified and characterized. Their size distribution has been measured, their internal properties have been studied. All of this traces back, in part, to the original discovery of the Botes void and the questions it raised. The tools of modern cosmology have also grown dramatically more sophisticated. N-body simulations that once modeled millions of particles can now model hundreds of billions, allowing detailed predictions of the cosmic web structure on scales from individual galaxies to the largest observable structures. Hydrodynamic simulations, which model not just dark matter, but also gas, star formation, feedback processes, and black hole growth, can now reproduce many of the observed properties of galaxies in different environments, including voids. Machine learning techniques are increasingly being applied to large-scale structure data, enabling the detection of structures and correlations that traditional methods might miss. Neural network-based void finders, topological data analysis tools that characterize the shape of the cosmic web without reference to specific structures, and simulation-based inference techniques that allow cosmological parameters to be measured from complex observational data. All of these are active areas of methodological development that are transforming what is possible in the study of the large-scale structure. The Botes void, discovered with relatively modest observational technology in the early 1980s, is in the process of being studied with tools and methods of a sophistication that the original discoverers could not have imagined. The void itself has not changed, but our ability to understand it, to characterize it, and to extract scientific information from it is growing rapidly. What remains genuinely unknown about the Botes void? Several things. First, its internal galaxy population is not fully characterized. The 60 galaxies identified within the void represent only those detected by surveys sensitive enough to find them at that distance. There may be additional dwarf galaxies, smaller, fainter systems that have not yet been detected. A complete census of the void's inhabitants would require a deep survey specifically targeting the Botes void region, something that has not yet been done. Second, the void's exact boundaries are not perfectly defined. The transition from the void to the surrounding cosmic web is gradual, and different definitions of where the void begins and ends can lead to different estimates of its size. More precise characterization of the density field in and around the void, mapping out exactly how the galaxy density varies from the void's interior to its surrounding walls and filaments, would sharpen the picture considerably. Third, the question of whether the Botes void's size is consistent with the standard cosmological model remains partly open. While current simulations can produce large voids, a definitive statistical comparison, one that accounts rigorously for observational selection effects and uses simulations with sufficiently large volumes, has not yet fully closed the question. Upcoming large-scale surveys will provide both better observational data and, by constraining cosmological parameters more tightly, enable more precise theoretical predictions. Fourth, the properties of the galaxies within the void, their star formation rates, gas content, morphologies, and evolutionary histories are poorly known compared to galaxies in average density environments. Detailed studies of even a few of the 60 void galaxies would provide valuable empirical data for models of galaxy formation in extreme environments. Fifth, and most fundamentally, the physics of the inflationary epoch that set the initial conditions for all of cosmic structure formation is still not fully understood. Inflation explains many observed features of the universe, but the specific model of inflation, the particle physics mechanism responsible for it, is unknown. Future measurements of the CMB polarization, particularly the B-mode polarization signal that would be produced by gravitational waves from inflation, may provide new constraints on inflationary models. These constraints would in turn affect predictions for the statistics of large-scale structure, including the size distribution of voids. The Botes void is thus embedded in some of the deepest open questions of modern physics and cosmology. It is at once a remarkable empirical discovery, a cosmological probe, a window into the physics of galaxy formation in extreme environments, and a reminder of the scale and character of the universe we inhabit. The universe is mostly empty. Its matter is organized into an intricate filamentary web threaded through a dominant volume of voids. The largest known void sits 700 million light-years away in the direction of the Boetes constellation, 330 million light-years across, containing almost nothing. It formed from a quantum fluctuation in the first tiny fraction of a second of the universe's existence, grew over billions of years as gravity drained matter away from it into the surrounding filaments, and will continue to expand as dark energy drives the cosmic web apart. Understanding it completely, its origin, its contents, its relationship to the rest of cosmic structure, and what it tells us about the fundamental physics of the universe, is an ongoing scientific project. One that began with a small team of astronomers noticing an anomalous gap in a survey of galaxy redshifts, and that continues today with the world's largest telescopes and most powerful supercomputers. The void is there, in the northern sky, in the direction of the Big Dipper. You cannot see it, but it is looking back. To understand what makes the Boite's void so scientifically compelling, it helps to go deeper into the mathematics and physics of structure formation, the process by which the smooth early universe gave rise to the intricate cosmic web we observe today. The universe, at the time of recombination, the epoch, approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, was nearly uniform in density. The CMB, which we observe as the thermal radiation from that epoch, shows temperature fluctuations of only about 30 microkelvins against a mean temperature of approximately 2,700 millikelvin. That is a fractional variation of about 1 part in 100,000. From this nearly smooth initial state, gravity had to build everything we observe today: stars, galaxies, galaxy clusters, superclusters, and the cosmic web, including voids as large as the Boite's void. The fact that it succeeded in doing so is a testament to the extraordinary power of gravity acting over billions of years, and to the specific properties of dark matter, which provided the gravitational scaffolding for structure formation. The role of dark matter in structure formation is crucial and worth explaining in some detail. In the standard cosmological model, dark matter is cold, meaning it was moving slowly compared to the speed of light at the epoch when it decoupled from the thermal plasma of the early universe. This has important consequences for structure formation. Cold dark matter can clump together on all scales, from very small to very large. It does not have the thermal pressure that prevents normal matter from collapsing on small scales. As a result, dark matter halos, gravitationally bound clumps of dark matter, can form on a wide range of scales, providing the gravitational wells into which normal matter subsequently falls. The cosmic web structure we observe is largely a reflection of the dark matter distribution. The filaments and sheets of the cosmic web are primarily dark matter structures, with visible galaxies and gas tracing the dark matter distribution. The voids are regions where the dark matter density is very low, and correspondingly, the density of visible matter is also very low. The growth of structure in the universe can be described mathematically using perturbation theory, the analysis of how small initial density fluctuations evolve over time under gravity. In the linear regime, where fluctuations are small, the growth of density perturbations is described by a simple differential equation whose solution depends on the cosmological parameters: the density of matter, the density of dark energy, and the Hubble constant. In the nonlinear regime, where density fluctuations have grown large and matter has collapsed into halos and filaments, the evolution is more complex and requires numerical simulations. The power spectrum of density fluctuations, which describes how much fluctuation power exists at each scale, evolves in a predictable way from its initial form set by inflation. At early times, fluctuations grow on all scales. As the universe expands and its matter content becomes less dominant relative to its radiation content in the early universe, and later relative to dark energy, the growth rate changes. The detailed shape of the power spectrum today, as measured through galaxy surveys, provides constraints on all of these cosmological parameters. Voids are particular probes of the power spectrum on large scales. The size distribution of voids, how many voids exist at each size, is sensitive to the amplitude of density fluctuations on scales comparable to the void sizes. A universe with more large-scale power would have more large voids. By measuring the void size function, the number of voids per unit volume, as a function of their radius, cosmologists can, in principle, constrain the amplitude of the matter power spectrum and other cosmological parameters. This is why the discovery and characterization of extreme voids, like the Boite's void, is not just a matter of astronomical curiosity, but a genuine cosmological measurement. Each very large void that is found and characterized adds to the statistical sample from which inferences about the power spectrum can be drawn. The physics of how voids evolve over time is also interesting. In the linear regime, underdense regions expand faster than the mean. The lower gravitational pull means they are less decelerated by gravity. As a result, voids grow over time. Matter drains out of them and accumulates in the surrounding filaments and sheets. In the nonlinear regime, the interiors of voids become increasingly underdense, and the void boundaries where the density transitions from void to filament become sharper. Simulations show that voids also interact with each other and with the surrounding large-scale structure. Small voids embedded within larger voids can merge over time, contributing to the growth of the larger void. Voids at the edges of filaments can be deformed by the tidal forces from adjacent structure. The evolution of the void population over cosmic time is a rich subject that modern simulations are well equipped to study. One prediction of this picture is that voids today should be at a certain characteristic expansion rate relative to the surrounding matter. Galaxies inside voids should on average be moving away from the void center, pushed by the slightly enhanced expansion rate of the underdense region. Galaxies near the void boundaries should on average be moving toward the void boundaries, evacuating the void interior. This distinctive velocity pattern, called the void outflow, has been detected observationally in large-scale structure surveys by analyzing the statistical distribution of galaxy velocities relative to identified voids. The amplitude of the void outflow is sensitive to the growth rate of cosmic structure, which in turn is sensitive to the theory of gravity on cosmological scales. In general relativity, the standard theory of gravity, the relationship between the distribution of matter and the growth rate of structure has a specific form. Alternative theories of gravity, proposed as modifications to general relativity, predict different growth rates and therefore different void outflow velocities. This makes void outflow measurements a potential test of general relativity on cosmological scales. Such a test is important because general relativity has been confirmed with extraordinary precision in the solar system and in binary pulsar systems. But these tests operate at scales many orders of magnitude smaller than the scales relevant to cosmic structure formation. It is possible, though there is no strong evidence for it, that gravity behaves differently at very large scales, and voids provide a way to probe this. The relationship between voids and weak gravitational lensing is another active area of research. Weak lensing refers to the slight distortion of the apparent shapes of distant galaxies caused by the gravitational deflection of light by intervening matter. This effect is typically discussed in the context of dark matter halos and galaxy clusters, which produce coherent distortions in the shapes of background galaxies that can be measured statistically. But underdense regions' voids also produce a weak lensing signal, of opposite sign to the signal from overdense regions. A photon passing through a void encounters less gravitational focusing than a photon passing through the mean density universe, and the images of background galaxies behind a void are slightly demagnified and have their shapes distorted in a characteristic pattern. Measuring this void lensing signal requires large samples of voids and large samples of background galaxies, but it is within reach of current and upcoming surveys. The void lensing signal directly probes the total matter distribution in the void, both dark and normal, and can be combined with spectroscopic measurements of the void galaxy distribution to test the relationship between the void lensing distribution of visible matter galaxies and the distribution of total matter, including dark matter. This relationship, called the galaxy bias, is a significant source of uncertainty in many cosmological measurements, and void lensing provides a way to calibrate it in the low-density regime. Taken together, the various cosmological uses of voids, void abundance constraints on the power spectrum, void outflow constraints on the growth rate, void lensing constraints on the matter distribution, and CMB void correlations through the integrated Sachs-Wolf effect, make voids one of the most versatile and powerful tools in the cosmologist's toolkit. The study of voids has evolved from a niche curiosity to a mainstream cosmological methodology. This evolution has been accompanied by the development of sophisticated void-finding algorithms. Identifying voids in large galaxy surveys is not trivial. Galaxies are not uniformly distributed, even in underdense regions. They exist as discrete points in redshift space, and the transformation from galaxy positions to a continuous density field introduces smoothing that can affect the shapes and sizes of identified voids. Redshift space distortions. The distortion of the apparent positions of galaxies along the line of sight due to their peculiar velocities complicate the geometry of voids in redshift space compared to real space. Various void-finding algorithms have been developed to address these challenges. Spherical underdensity finders identify the largest sphere that can be placed in a region with a density below a specified threshold. Watershed algorithms treat the density field as a landscape and identify voids as the basins in that landscape, separated from neighboring basins by ridges. Tessellation-based methods use the geometry of the Voronoi tessellation of the galaxy distribution to identify underdense regions. Each method has different properties, sensitivities, and systematic biases. The comparison of void catalogs produced by different methods, applied to the same survey data, reveals how much the inferred void population depends on the algorithm used. This kind of systematic comparison is important for ensuring that scientific conclusions drawn from void analyses are robust. The Botez void is large enough and empty enough that its identification does not depend sensitively on the specific algorithm used. Any reasonable void finder applied to a survey covering its sky location and depth will identify it as a prominent underdense region. But for the general population of smaller voids used in statistical analyses, the choice of algorithm and its parameters matters a great deal. Modern void analyses use MOC's simulated galaxy catalogs drawn from n-body simulations, processed to mimic the properties of the observed survey to characterize the systematic effects of the void-finding algorithm, and to calibrate the inferences drawn from the void population. This pipeline, from simulation to MOC catalog to void finding to statistical analysis, is now well established in the field. As we move forward in time, the picture of cosmic structure painted by these analyses will continue to sharpen. The Dark Energy Spectroscopic Instrument, now in operation at the Kitt Peak National Observatory in Arizona, is the current state-of-the-art in spectroscopic galaxy surveys. It uses 5,000 robotically positioned optical fibers to simultaneously measure the spectra and therefore redshifts of 5,000 galaxies at once across a wide field of view. Over its 5-year primary survey, DESI aims to measure the spectra of approximately 40 million galaxies and quasars, producing the most detailed 3-dimensional map of the universe yet created. This map will contain an enormous number of voids, far more than have been identified in any previous survey. The void size function, the void lensing signal, the void outflow, and the CMB void cross-correlation will all be measurable with unprecedented precision. Whether the Botez void sits comfortably within the statistical distribution predicted by the standard cosmological model, or whether it remains an outlier requiring special explanation, will be much clearer after DESI has completed its survey and produced its void catalog. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting a complementary survey from space, free of the atmospheric distortions that affect ground-based measurements. Euclid measures both galaxy shapes for weak lensing and galaxy spectra for redshifts across roughly 1/3 of the sky. Its combination of high image quality and wide-field spectroscopy makes it uniquely powerful for void lensing analyses, the signal that directly maps the total matter distribution in and around voids. The combination of DESI spectroscopic data and Euclid lensing data will enable measurements that neither instrument could achieve alone. By cross-correlating the void catalogs from DESI with the lensing signal measured by Euclid, cosmologists will be able to constrain the relationship between galaxy positions and total matter distribution with much greater precision. This cross-survey analysis is one of the most anticipated scientific programs in current observational cosmology. Looking further ahead, the Vera-C Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is currently in the process of first light and commissioning at its site in the Andes Mountains of Chile. With a primary mirror 8.4 meters in diameter and a 3 billion pixel camera with a field of view covering 9 square degrees of sky, Rubin will conduct the Legacy Survey of Space and Time, a 10-year program imaging the entire accessible sky, roughly once every few nights. Over the course of the survey, it will detect tens of billions of individual objects and will build up exquisitely precise measurements of the shapes and positions of billions of galaxies. The Rubin survey will produce a photometric redshift catalog, estimated redshifts based on galaxy colors rather than spectroscopic measurements for billions of galaxies. While photometric redshifts are less precise than spectroscopic ones, the enormous number of galaxies detected will enable statistical analyses of the large-scale structure with unprecedented power. Void finding in photometric surveys requires adapted methods that account for the large redshift uncertainties, but these methods have been developed and tested, and the Rubin Void Catalog will be among the richest ever produced. The Square Kilometre Array, under construction in South Africa and Australia, will conduct the deepest and widest radio surveys of the sky ever achieved. Its primary scientific goals include measuring the distribution of neutral hydrogen gas across cosmic time, a tracer of the gas reservoir available for star formation, and detecting tens of millions of radio galaxies across the PRACE observable universe. The SKA will also serve as an extraordinarily precise detector of pulsar timing pulses from rotating neutron stars, so regular that they can be used as cosmic clocks, enabling the detection of gravitational waves at nanohertz frequencies through the pulsar timing array technique. These gravitational waves, produced by merging supermassive black hole binary systems, carry information about the large-scale structure of the universe and the rate of black hole mergers across cosmic time. The confluence of these observational programs will produce a scientific windfall for the study of large-scale structure, including voids. The Botes void, along with the broader population of cosmic voids, will be studied with a precision and a completeness that was unimaginable when it was first discovered in 1981. It is perhaps fitting to conclude by returning to the human scale to what the existence of the Botes void means for our understanding of where we are and what surrounds us. We live on a small, rocky planet orbiting an ordinary star, one of approximately 200 billion stars in the Milky Way. The Milky Way is one of approximately 2 trillion galaxies in the observable universe. All of these galaxies, all of their stars and planets and gas and dust, all of the dark matter that gravitationally binds them together, all of this constitutes only about 5% of the total energy content of the universe. The rest is dark matter at approximately 27% and dark energy at approximately 68%. The observable universe spans approximately 93 billion light-years in diameter. Within this volume, the matter is organized into a cosmic web of filaments and sheets, separated by voids. By volume, the voids dominate. They constitute roughly 80% of the volume of the observable universe. The largest void we have found, the Botes void, 330 million light-years across, is, by the standards of the universe, just one of many. It is the largest we have identified in the portion of the universe we have surveyed, but there may be others of comparable or greater size in regions we have not yet mapped in detail. As surveys extend deeper and cover more of the sky, the census of very large voids will become more complete. What the Botes void represents, more than anything else, is a reminder of the scale and emptiness of the cosmos. The universe is vastly larger than our everyday experience prepares us for. It is mostly dark, mostly empty, mostly cold. The warmth and complexity of planets and stars and living organisms are concentrated in a thin filamentary scaffolding that occupies only a small fraction of the total volume. This is not a cause for existential anxiety. It is simply the character of the universe we inhabit, one that became apparent to us only in the last century of scientific investigation, and that continues to reveal new details and new depths as our observational and theoretical tools improve. The Botes void was first detected as an absence, a gap in a catalog of galaxy redshifts, noticed by a small team of astronomers working on a survey of the large-scale structure. Since then, it has become a subject of active scientific investigation, a cosmological probe, a test of theories of gravity and dark energy, and a window into the history of the universe. It will continue to be studied for decades to come, and the science it enables will deepen our understanding of the cosmos in ways we cannot yet fully anticipate. In the meantime, it remains there, 700 million light-years away, in the direction of Botes, bounded by the threads of the cosmic web occupying 330 million cubic light-years of nearly perfect emptiness, the largest known nothing in the universe. The history of how we came to understand the universe's large-scale structure is itself a story worth telling in depth, because it illustrates how scientific understanding develops through the accumulation of observations, the development of theoretical frameworks, the conflict between prediction and data, and the eventual convergence on a coherent picture. In the 1950s and 1960s, the dominant picture of the universe's large-scale structure was relatively simple. Galaxies clustered into groups and clusters were distributed more or less randomly on larger scales. There were some known superclusters regions of enhanced galaxy density on scales of tens of millions of light-years, but these were thought to be the largest significant structures. This picture began to change with the work of Gérard de Vaucouleurs in the 1950s and 60s. De Vaucouleurs argued, based on his observations of galaxy distributions, that the local region of the universe is part of a large, flattened supercluster, the local supercluster, later renamed the Virgo supercluster after the Virgo cluster at its center. He was largely correct, but his claims were initially controversial because they seem to violate the assumption that the universe was uniform on large scales, on the cosmological principle. In the 1970s, the development of more systematic redshift surveys allowed the three-dimensional distribution of galaxies to be mapped for the first time. The work of Robert Kirshner and his collaborators at the Harvard-Smithsonian Center for Astrophysics, along with the work of Mark Davis and collaborators, began to reveal a universe with more structure than previously appreciated. Galaxies were not randomly distributed. They formed filaments and sheets, with large empty regions between them. The discovery of the Botez void in 1981 was a crystallizing event in this evolving picture. It showed that the empty regions, the voids, were not just minor gaps between clusters, but enormous spaces that dominated the volume of the universe. The void was so large that it attracted immediate attention and motivated further surveys to characterize the large-scale structure more completely. The work that followed in the 1980s was remarkable. The Center for Astrophysics survey, led by Margaret Geller and John Hutra, among others, systematically mapped the redshifts of thousands of galaxies in slices of the sky. In 1986, their survey of the first complete slice produced one of the most famous images in cosmology, the so-called stickman or stickman figure, a map of galaxy positions in a thin slice of the sky that showed galaxies arranged in elongated filaments and sheets surrounding large, empty regions. The filaments formed a recognizable pattern of interconnected structures, and the voids between them were clearly enormous. This image, a simple scatter plot of galaxy positions in right ascension versus recession velocity, changed how cosmologists visualize the universe. It made the cosmic web tangible in a way that abstract statistics could not. It showed that the universe had a sponge-like or foam-like structure on scales of tens to hundreds of millions of light years. And it demonstrated that this structure was not a minor correction to a uniform distribution, but its dominant character. The stickman figure became one of the most reproduced images in the history of cosmology. It appeared in textbooks, popular science articles, and public lectures. It helped establish the cosmic web as the organizing concept for understanding the universe's large-scale structure, and it stimulated a huge amount of theoretical work aimed at explaining how gravity could have produced such a complex pattern from the smooth initial conditions of the early universe. The theoretical framework that emerged from this work, the cold dark matter model of structure formation, refined to include dark energy in what became the lambda CDM model, has proven extraordinarily successful. It predicts the observed power spectrum of density fluctuations. It predicts the statistics of galaxy clusters. It predicts the distribution of void sizes. It predicts the acoustic oscillation signal seen in the CMB and in galaxy surveys. And it predicts the accelerating expansion of the universe, confirmed through supernova observations in 1998. The lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, is now the standard model of cosmology. Its parameters have been measured to percent-level precision from a combination of CMB data, galaxy survey data, supernova data, and measurements of the local expansion rate. It is arguably the most precisely tested and confirmed physical model in science, with the possible exception of the standard model of particle physics. Yet it leaves important questions unanswered. The physical nature of dark matter is unknown. Decades of searches for dark matter particles using underground detectors, collider experiments, and indirect astrophysical observations have not definitively detected a dark matter particle. The physical nature of dark energy is equally mysterious. The cosmological constant, while mathematically simple, has a value that is extraordinarily difficult to explain from first principles in particle physics. The so-called cosmological constant problem is one of the deepest unsolved problems in theoretical physics. There are also tensions between different measurements of the Hubble constant, the current rate of expansion of the universe. Measurements from the CMB, which probe the early universe and extrapolate to the present expansion rate assuming the lambda CDM model, give a value around 67 to 68 kilometers per second per megaparsec. Measurements from the local universe using supernovae calibrated with Cepheid variable stars give a value around 73 kilometers per second per megaparsec. This discrepancy, called the Hubble tension, is statistically significant and has been confirmed by multiple independent measurements. It may indicate systematic errors in one or both types of measurement, or it may indicate new physics beyond the standard lambda CDM model. If the Hubble tension reflects genuine new physics, perhaps additional radiation-like components in the early universe, or modifications to the standard model at early times, then predictions for the large-scale structure of the universe would be possible. including the void size distribution, would need to be revisited. The Botez void and other large voids could potentially provide an independent consistency check on models proposed to resolve the Hubble tension. Similarly, the growth tension, a discrepancy between the amplitude of matter clustering inferred from CMB data and the amplitude measured from weak lensing surveys, could, if it persists, indicate modifications to the standard model of structure growth. Void statistics, which probe structure on large scales in the low-density regime, are sensitive to modifications of this kind and could provide important discriminating power between competing models. The universe is asking hard questions through its large-scale structure, and the Botez void is one of the most emphatic parts of that structure. Its existence is a fact that any successful cosmological model must accommodate. Whether the current standard model accommodates it fully, or whether the void's extreme size hints at physics not yet incorporated into our theoretical framework, remains to be seen. The history of cosmology is full of instances where anomalies, observations that did not fit comfortably into the prevailing theoretical framework, turned out to be the leading edge of a deeper understanding. The anomalous rotation curves of spiral galaxies, which showed that stars at the outer edges of galaxies orbit faster than the visible mass distribution would predict, led to the inference of dark matter. The anomalous dimness of distant supernovae, which showed that the universe's expansion was accelerating rather than decelerating, led to the discovery of dark energy. The Hubble tension may be the next such anomaly, pointing toward new physics that we have not yet identified. The Botez void may or may not be in this category. It may be fully consistent with the standard model as a statistical outlier, the largest void in the observable universe that happened to fall within the volume we have surveyed. Or it may represent a genuine challenge to our understanding of structure formation. The answer will come from better data, more sophisticated analysis, and more detailed comparison with theoretical predictions. This is the process of science, the accumulation of observations, the development of theories, the testing of predictions, and the revision of understanding in the light of new evidence. The Botez void is one data point in this ongoing process, a particularly striking and evocative one, but a data point nonetheless. And yet there is something more to it than its scientific significance alone. There is the sheer scale of it. 330 million light-years, 700 million light-years from Earth, 60 galaxies scattered across a volume that could contain thousands. The temperature of space, less than 3 degrees above absolute zero. The absolute darkness, the absence of reference points, the pure void. There is something that the human mind struggles to hold when confronted with these numbers. We evolved to navigate environments measured in meters and kilometers. We understand space at the scale of a room, a city, a continent. We can extend our intuition to the scale of the solar system with some effort, but the scale of galaxies, the scale of the cosmic web, the scale of the Botez void, these exceed what intuition can comfortably grasp, and yet they are real. The void is there. Its scale can be calculated from first principles. Its distance can be measured from the redshift of galaxies at its boundary. Its size can be mapped by surveying those boundaries. These are not speculative estimates, but observational measurements, as solid as any other empirical facts in science. The universe is structured in a way that our daily experience gives us no preparation for. The scales are incomprehensible in terms of human experience, but comprehensible in terms of physics. The void formed because gravity pulled matter away from it over billions of years. It will continue to grow as dark energy drives the surrounding filaments apart. It is the predictable consequence of physical laws operating over cosmic time. Understanding it fully, quantitatively, in the context of the lambda CDM model and its potential extensions, is one of the challenges of 21st century cosmology. The tools to meet that challenge are being built now. The surveys are underway. The simulations are running. The analyses are being developed. The Botez void will continue to be studied. Its secrets, such as they are what its exact size tells us about the matter-power spectrum, what its 60 galaxies tell us about evolution in extreme environments, what its existence tells us about the statistical properties of the cosmic web, will be extracted through careful, patient, rigorous scientific work. And in the meantime, it is there, in the northern sky, between the Big Dipper and Arcturus. 700 million light-years away, 330 million light-years across, mostly empty, mostly dark, mostly silent. The largest known nothing in the observable universe. To fully appreciate the scientific context of the Botez void, It is worth exploring in greater depth the relationship between the void and the cosmic microwave background, and the specific ways in which large voids have become tools for probing fundamental physics. The cosmic microwave background is the most precisely measured phenomenon in all of observational cosmology. It was first detected accidentally in 1964 by Penzias and Wilson, but it was the COBE satellite, launched in 1989, that produced the first precise all-sky map of the CMB and confirmed that its temperature was uniform to 1 part in 100,000. This result won John Mather and George Smoot the Nobel Prize in Physics in 2006. The slight variations in the CMB temperature, the pattern of hot and cold spots across the sky, encode the state of the universe at the time of recombination. The slightly denser regions that would eventually become the galaxy clusters and superclusters of the cosmic web were slightly hotter at recombination. The slightly less dense regions that would eventually become voids were slightly cooler. These temperature variations were at the level of 30 microkelvins against a mean temperature of about 2,700 millikelvin. After COBE established the existence of CMB temperature anisotropies, the WMAP satellite, launched in 2001, produced higher resolution maps that revealed the detailed structure of these anisotropies and enabled precise measurements of the cosmological parameters. WMAP measured the geometry of the universe, confirming that it was flat to high precision, and determined the densities of matter, and dark energy with percent-level accuracy. The Planck satellite, launched in 2009 by the European Space Agency, produced the most precise CMB maps yet obtained, with angular resolution more than 3 times better than WMAP and significantly better sensitivity. The Planck results confirmed and refined the lambda CDM cosmological model, and they identified several anomalies in the CMB that remain subjects of active investigation. One of these anomalies, the CMB cold spot, mentioned earlier, has been proposed to be related to a supervoid. But there is another aspect of the CMB void connection that is worth exploring: the statistical signature of the entire void population on the CMB through the integrated Sachs-Wolf effect. The integrated Sachs-Wolf effect arises because the gravitational potentials in the universe change over time in a dark energy-dominated universe. In a matter-dominated universe without dark energy, gravitational potentials would remain constant over time, on large scales, and CMB photons would not gain or lose net energy as they pass through these potentials. In a universe with dark energy, however, the accelerating expansion causes the gravitational potentials to decay. They become shallower over time. A photon climbing out of a potential well that has become shallower than when the photon entered will gain net energy. A photon passing through an underdense region, a void, which has a negative potential, will lose a small net amount of energy compared to what it would lose in a universe without dark energy. The net effect is that photons passing through large-scale overdensities gain a small net energy, leave a slightly warm imprint on the CMB, while photons passing through large-scale underdensities lose a small net energy, leave a slightly cool imprint on the CMB. This is the integrated Sachs-Wolf effect, and it is a direct probe of dark energy because it requires the decay of gravitational potentials, which only occurs in a universe dominated by dark energy. The integrated Sachs-Wolf effect has been detected statistically by cross-correlating the CMB temperature map with the distribution of galaxies in large-scale structure surveys. Because galaxies trace the density field, dense regions have more galaxies. Underdense regions have fewer. The cross-correlation of galaxy positions with CMB temperature provides a statistical measure of the integrated Sachs-Wolf effect. This cross-correlation has been detected at modest statistical significance in multiple surveys, providing an independent line of evidence for dark energy. The Boate's void is large enough and empty enough that it might produce a detectable, integrated Sachs-Wolf imprint on its own, without the need for stacking or cross-correlation analyses. Detecting the CMB imprint of the Boate's void alone would be extremely challenging given its angular extent and the noise in current CMB maps, but it is not inconceivable that future, more sensitive CMB experiments might attempt such a measurement. Beyond the integrated Sachs-Wolf effect, voids are also probed through the kinematic Sunyaev-Zeldovich effect. The kinematic Sunyaev-Zeldovich effect is a distortion of the CMB spectrum produced by the motion of gas relative to the CMB rest frame. Hot gas in galaxy clusters produces a well-known thermal Sunyaev-Zeldovich effect, a spectral distortion in which CMB photons are inverse Compton, scattered by the hot electrons in the intracluster medium, shifting photons from low to high frequencies and producing a characteristic spectral signature. The kinematic Sunyaev-Zeldovich effect is different. It arises from the bulk motion of gas, which produces a slight shift in the CMB temperature in the direction of the motion. Gas moving away from the observer shifts CMB photons to lower temperatures. Gas moving toward the observer shifts them to higher temperatures. By measuring the kinematic Sunyaev-Zeldovich effect in the directions of known galaxy clusters and voids, cosmologists can map the bulk velocity field of matter on large scales, another probe of the growth rate of structure and the properties of dark energy. The outflow of matter from voids, the tendency for galaxies and gas within voids to be moving away from void centers, produces a characteristic kinematic Sunyaev-Zeldovich signal that can, in principle, be measured by stacking CMB temperature maps in the directions of many voids from a problem galaxy survey. This measurement has been attempted and detected in recent years using data from the Planck satellite and ground-based CMB experiments like the Atacama Cosmology Telescope and the South Pole Telescope. Combined with galaxy surveys, the sensitivity of these measurements will improve dramatically with next-generation CMB experiments. The Simons Observatory, currently being built in the Atacama Desert of Chile, and CMB S4, a proposed network of ground-based CMB telescopes covering a wide range of sky with arc-minute resolution and extremely high sensitivity, will measure the kinematic Sunyaev-Zeldovich effect with much greater precision than current instruments. The combination of these CMB experiments with DESI, Euclid, and Rubin will enable simultaneous mapping of the large-scale velocity field and the large-scale density field, a powerful constraint on the physics of structure growth. The relationship between the large-scale velocity field and the density field is described in general relativity by a specific mathematical relationship, the continuity equation and the Euler equation of fluid mechanics applied to the cosmic matter field. Modified theories of gravity generally predict different relationships. By comparing the measured velocity field with the measured density field, using voids and their outflows as the observational probe, cosmologists can test whether the universe obeys the predictions of general relativity on cosmological scales. This test is one of the most fundamental possible in modern cosmology. General relativity has passed every test it has been subjected to in the solar system and in binary pulsar systems. But these tests operate at scales billions of times smaller than the scales relevant to the cosmic web. Extending the tests to cosmological scales requires using the large-scale structure itself as a laboratory, and voids are one of the cleanest environments in which to conduct this experiment. The reason voids are particularly useful for tests of gravity is that their dynamics are dominated by one force, gravity, with minimal contamination from baryonic physics, the complex processes involving gas, star formation, and feedback that complicate the interpretation of observations in dense environments. A galaxy cluster is a complex astrophysical object whose properties reflect a combination of dark matter dynamics, gas dynamics, stellar feedback, and active galactic nucleus feedback. A void is simpler. It is defined primarily by the absence of matter, and its dynamics are dominated by the large-scale gravitational potential. This simplicity makes voids attractive for precision cosmology. Their statistical properties, their abundance, their profiles, their velocity fields, can be predicted from first principles with relatively few theoretical assumptions, and discrepancies between predictions and observations are easier to interpret. There is also a growing field focused on using voids as probes of neutrino masses. Neutrinos are subatomic particles produced in radioactive decays and in nuclear reactions in stars. They interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect, but also making them uniquely interesting cosmological probes. Neutrinos have mass effect established through the observation of neutrino oscillations, the quantum mechanical process by which neutrinos change flavor as they travel, but the absolute values of the neutrino masses are not yet known. In cosmology, massive neutrinos suppress the growth of structure on scales below the neutrino free-streaming length, the scale at which neutrinos, moving freely through the universe, have traveled since the Big Bang. The free streaming suppresses the clumping of matter on small scales, smoothing out density fluctuations. This effect is sensitive to the sum of neutrino masses. Heavier neutrinos suppress more structure. Voids are sensitive probes of this suppression because they form in underdense regions. In a universe with more massive neutrinos, the density contrast between voids and filaments would be slightly smaller. The smoothing effect of neutrino free streaming would reduce the amplitude of density fluctuations, making the cosmic web slightly less pronounced. By measuring the statistical properties of voids, particularly their size, function, and their density profiles, cosmologists can constrain the sum of neutrino masses. The current generation of surveys is not yet precise enough to detect the effect of neutrinos on the void population with high significance. But the next generation DESI, combined with Euclid and Rubin, may achieve the necessary sensitivity. Measuring the neutrino mass from cosmological observations would be a landmark result in physics, complementary to the direct laboratory measurements using beta decay and neutrinoless double beta decay experiments. All of these potential measurements, dark energy constraints, growth rate tests, modified gravity tests, neutrino mass constraints depend on the existence and precise characterization of a large sample of cosmic voids. The Boites void, as the largest known void, serves as a remarkable demonstration of just how extreme the cosmic web's emptiest regions can be. But for statistical cosmological applications, what matters is the population of voids at all sizes, measured over the largest possible volume. It is also worth discussing the relationship between voids and the reionization of the universe. The epoch when the first stars and galaxies formed, and their ultraviolet radiation, ionized the neutral hydrogen that had filled the first age. Universe since recombination. Reionization began somewhere between about 100 million and 500 million years after the Big Bang, and was largely complete by about 1 billion years after the Big Bang, when the universe was roughly 7% of its current age. The process of reionization was not uniform. The first sources of ionizing radiation, young, massive stars, and the precursors of the supermassive black holes, now found at the centers of massive galaxies, formed in the densest regions of the emerging cosmic web. From these sources, bubbles of ionized gas grew outward, eventually merging to fill the universe completely. In void regions, the underdense regions of the early cosmic web, there were fewer sources of ionizing radiation. Reionization, therefore, proceeded more slowly in the precursors of today's voids. The last neutral hydrogen pockets to be ionized were in the lowest density regions, the early voids. This differential timing of reionization across different environments left an imprint on the CMB through the kinematic Sunyaev-Zeldovich effect and on the distribution of neutral hydrogen that the Square Kilometre Array and its precursor instruments are now beginning to probe. Understanding the connection between the early cosmic web, the process of reionization, and the evolution of the void population over cosmic time is an active area of research that bridges cosmic structure formation and the physics of the first galaxies. The observations required detecting the faint signal of neutral hydrogen in the early universe through its emission and absorption of radio waves are among the most technically challenging in all of observational astrophysics. The Boites void, as a mature structure in the present-day universe, is the end product of billions of years of evolution from the underdense regions of the early cosmic web. Its ancestor void, the precursor underdense region at the time of recombination, would have been among the last regions to be reionized. The 60 galaxies within the Boites void today formed from the sparse gas that remained in the void after the surrounding cosmic web had drained most of the matter away. They are, in a sense, the survivors, the small fraction of matter that formed galaxies even in the most underdense environment in the known universe. Studying these galaxies, understanding their formation histories, their stellar populations, their gas content would not only shed light on galaxy formation in extreme environments, it would also provide a window into the early evolution of the void itself, how the underdense region evolved from a slight deficiency in the early universe to the dramatic emptiness of the Boites void today. This is the deep connection between the large-scale structure we observe today and the initial conditions set in the first moments after the Big Bang. Every structure in the universe, every galaxy, every cluster, every void, traces back to those initial conditions, evolved over 13.8 billion years by the known forces of physics. Understanding the largest void in the known universe is, ultimately, a way of reading the history of the universe itself. That history is written in the distribution of galaxies across the sky, in the temperature anisotropies of the CMB, in the motions of galaxies as measured through redshift surveys, and in the shapes of galaxies as measured through weak lensing. The Boites void is one of the most dramatic chapters in that history, a region that tells us about the cumulative effect of gravity over cosmic time, about the properties of dark energy, and about the statistical character of the initial quantum fluctuations from which all structure grew. 45 years after its discovery, the Boites void remains one of the most scientifically productive and scientifically challenging features of the observable universe. The questions it raises about its formation, its contents, and its relationship to the fundamental physics of the cosmos remain open. They are being actively investigated with the most powerful observational and theoretical tools available. And as those tools improve, as the surveys grow larger, as the simulations grow more detailed, as the theoretical frameworks become more precise, the answers will come. Slowly, as scientific answers always come. But they will come. The void is waiting. There is one more dimension of the Boite's void that deserves careful attention. The question of whether, in the fullness of cosmic time, voids, like this one, might themselves become the seeds of future structure, or whether they are simply the permanent scars of matter that has left and will never return. In the current epoch of the universe, voids are expanding. The dark energy that dominates the universe's energy budget is causing the expansion to accelerate, and this acceleration is most pronounced in the underdense regions. The surrounding filaments and walls, which are gravitationally bound, resist the expansion, but the voids themselves, containing almost no mass, to gravitationally counteract the expansion grow as the universe expands. On very long timescales, tens of billions of years into the future, the picture changes dramatically. Dark energy will continue to drive the expansion of the universe. The distances between galaxy clusters, the gravitationally bound objects that will persist, will increase exponentially. Objects that are not gravitationally bound will recede beyond the observable horizon. The cosmic web, as a connected structure, will effectively dissolve as the universe expands. In this far future, each gravitationally bound structure, each galaxy group, each galaxy cluster will be an island, isolated from all others by the accelerating expansion. The local group of galaxies, the Milky Way, Andromeda, the Magellanic Clouds, and the other smaller members will remain gravitationally bound together, eventually merging into a single large elliptical galaxy over a timescale of several billion years. But beyond the local group, all other galaxies will recede into the darkness. In this scenario, the Boite's void will have expanded to engulf not just its current 330 million light-year interior, but progressively more of the universe as the expansion accelerates. The filaments bounding the void will themselves thin out as galaxies within them recede, and as the overall structure of the universe becomes sparser. The concept of a void, defined as a region significantly emptier than the mean, will become less meaningful as the entire universe becomes emptier. The maximum entropy state of the universe, on timescales of 10 to the 100 years or more, is one in which all matter has been converted to photons and leptons through the decay of protons. If protons are unstable, which they may be, or through the evaporation of black holes over astronomical timescales through Hawking radiation. The large-scale structure, the cosmic web, the voids, the clusters, will be completely erased. The information encoded in the distribution of matter across the universe, including the information encoded in the Boite's void, will be dispersed. This is, of course, a description of the very far future timescales, so long that the current age of the universe is negligible in comparison. But it is worth contemplating because it underscores how special the current epoch is. The universe today is in a state where its large-scale structure is mature, observable, and scientifically tractable. The observations we are making now, the maps we are building, the cosmological parameters we are measuring, all of this will eventually be lost as the observable universe shrinks and the structures within it dissolve. The Boite's void is not merely a scientific curiosity. It is part of the fleeting snapshot of cosmic structure that exists in the current epoch, available to be studied by the civilizations that happen to exist at this moment in the universe's history. We are fortunate to be able to see it. Turning from the far future to the more immediate scientific agenda, it is worth reviewing the specific observational programs currently underway or planned that will most directly improve our understanding of the Boite's void and of cosmic voids in general. The Dark Energy Spectroscopic Instrument Survey, which began its full 5-year primary survey in 2021, will by its completion have measured spectroscopic redshifts for roughly 40 million galaxies and quasars, over roughly 14,000 square degrees of sky, about 1/3 of the full sky. This includes the sky region covering the Boite's void and its surroundings. The DESI Galaxy Catalog will provide the most detailed 3-dimensional map of the cosmic web in this region of the sky, enabling precise characterization of the void's boundaries, its internal galaxy population, and its relationship to the surrounding large-scale structure. DESI also uses quasars, extremely luminous active galactic nuclei, powered by accretion onto supermassive black holes, as tracers of the large-scale structure at higher redshifts. At the distance of the Botez void, which corresponds to a redshift of approximately 0.07, the primary tracers are luminous red galaxies and emission line galaxies. Both of these galaxy populations are well suited for precise redshift measurements with DESI's spectrographs. The Euclid satellite, launched in July 2023, is conducting its wide-field survey in the near, infrared, and optical. Euclid's primary science goals are measuring the dark energy equation of state and the growth of structure through weak gravitational lensing and spectroscopic redshift surveys. The Euclid-wide survey covers approximately 15,000 square degrees of sky, including the Botez region. Euclid will measure the shapes of billions of galaxies with high precision, enabling weak lensing analyses of the matter distribution in and around the Botez void. The combination of DESI's spectroscopic redshifts, which precisely locate galaxies in three-dimensional space, with Euclid's lensing measurements, which probe the total matter distribution, including dark matter, will enable joint analyses of the void that are far more powerful than either dataset alone. Such joint analyses can constrain the galaxy bias, the neutrino mass, the dark energy equation of state, and the growth rate of structure simultaneously. The Rubin Observatory's Legacy Survey of Space and Time, expected to begin full operations in the mid-2020s, will add even greater depth and sky coverage to the photometric galaxy catalog. With its extraordinary depth detecting galaxies about 4 times fainter than Euclid per night of observation and its cadence-based approach that will produce a movie of the sky over 10 years, Rubin will find billions of galaxies in the region of sky covering the Botez void, and will measure their photometric redshifts with higher precision than any previous survey. The James Webb Space Telescope, operational since early 2022, has already demonstrated its ability to observe galaxies at extraordinary distances and to characterize their stellar populations and star formation histories with unprecedented detail. While the Botez void's galaxies are too faint for routine JWST spectroscopy, targeted observations of the brighter void galaxies, perhaps 10 to 20 hours of telescope time per galaxy, would yield detailed information about their stellar populations, gas content, and kinematics. Such observations, if prioritized, would represent a unique scientific opportunity to study galaxy evolution in the most extreme low-density environment observable. The Square Kilometer Array, whose construction is underway with an expected first science date in the mid-2020s for the SKA Low Array in Australia and slightly later for SKA Mid in South Africa, will survey neutral hydrogen in galaxies out to high redshifts. The neutral hydrogen content of galaxies, their cold gas reservoir, is a key indicator of their capacity for future star formation. In void environments, galaxies are expected to have retained more of their original gas compared to cluster galaxies, which lose gas through interactions and ram pressure stripping. Measuring the neutral hydrogen content of the Botez void galaxies with the SKA would test this prediction directly. The Next Generation Very Large Array, a proposed radio telescope facility in North America that would significantly expand on the capabilities of the existing Carl G. Jansky Very Large Array, would provide even higher resolution and sensitivity radio observations of the void galaxies and their environments. While still in the planning and development stage, the NGVLA would be capable of mapping the radio continuum emission from synchrotron radiation associated with cosmic ray electrons in galaxy magnetic fields, and molecular gas emission from carbon monoxide and other molecules in the void galaxies with high resolution. All of these facilities, individually and in combination, are contributing to a progressively more complete picture of the Botez void and its scientific significance. What began as a gap in a redshift survey in 1981 is becoming, decade by decade, a precisely characterized cosmological structure that serves as a laboratory for testing fundamental physics. The scientific story of the Botez void is still being written. The surveys are still mapping it. The simulations are still modeling it. The theorists are still working to understand its formation and evolution. The observations of its galaxies are still incomplete. The cosmological inferences from its properties are still being extracted. But the outline of that story is clear enough to see. The Botez void formed from a quantum fluctuation in the inflationary epoch of the very early universe. Gravity amplified that fluctuation over billions of years, draining matter out of the underdense region and into the surrounding filaments and superclusters. Dark energy accelerated the expansion of the universe and cause the void to grow faster than it would have in a purely matter-dominated cosmos. Today, the void spans 330 million light-years, contains roughly 60 galaxies in a single interior filament, and sits 700 million light-years from Earth in the direction of the Boötes constellation. It is the largest known void in the observable universe. It is a probe of dark energy, of the growth rate of structure, of the neutrino mass, and of the properties of gravity on cosmological scales. It is a laboratory for studying galaxy evolution in the most extreme low-density environment accessible to current observations. And it is a reminder that the universe we inhabit is mostly empty, that the stars and galaxies that seem to fill the sky are arranged in thin, filamentary scaffolding stretched across a dominant volume of void. Understanding the Boötes void is, ultimately, part of the broader project of understanding the universe itself. Its origin, its composition, its structure, its evolution, and its fate. It is a project that has been underway for centuries, and that will continue for centuries more. The void is there. We are here, and the work of understanding continues. One of the most fascinating aspects of void science that has emerged in recent years is the application of topological methods to characterize the large-scale structure. Topology, the branch of mathematics concerned with properties of space that are preserved under continuous deformation, provides tools for describing the shape and connectivity of the cosmic web in ways that traditional statistical measures cannot. The Euler characteristic, Betti numbers, and persistent homology are topological descriptors that capture information about the connectivity, the number of independent loops, and the number of enclosed voids in a three-dimensional point, set precisely the kind of information relevant to the cosmic web. By computing these descriptors from galaxy survey data and comparing them to predictions from cosmological simulations, researchers can extract cosmological information that is complementary to traditional power spectrum analyses. Persistent homology, in particular, is well suited to the analysis of voids. It identifies topological features in this case, the three-dimensional enclosed voids in the galaxy distribution that persist across a range of density thresholds. A feature that persists for a wide range of thresholds corresponds to a genuine, robust structure, while a feature that appears and disappears within a narrow threshold range is more likely to be a statistical fluctuation. This persistence information can be used to define and characterize voids in a way that is more robust to noise and survey effects than traditional methods. Applications of persistent homology to galaxy surveys have demonstrated that the topological properties of the cosmic web, the distribution of void sizes and shapes, as characterized by persistent homology, are sensitive to cosmological parameters and can be used to test cosmological models. This is a relatively new field, and the full potential of topological methods for cosmological inference is still being explored. The Boötes void, as the largest known void, would be among the most prominent features identified by any topological analysis of the large-scale structure in its region of the sky. Its persistence, its continued prominence across a wide range of density thresholds, is a reflection of its genuine extreme underdensity, not a statistical artifact. Another emerging approach is the use of machine learning and artificial intelligence to analyze large-scale structure data. Traditional statistical analyses of galaxy surveys rely on summary statistics, the power spectrum, the correlation function, the void size function that compress the information in the data into a limited set of numbers. These statistics capture some of the cosmological information in the data, but not all of it. The full probability distribution of galaxy positions, conditioned on the cosmological parameters, contains more information than any finite set of summary statistics. Neural network-based approaches can, in principle, extract more of this information. A neural network trained on simulated galaxy catalogs can learn to recognize the statistical signature of different cosmological parameters in the galaxy distribution, and when applied to observed data, it can extract cosmological constraints that are more powerful than those from traditional methods. Several groups have applied machine learning to the identification and characterization of cosmic voids with promising results. Neural network void finders can identify voids in noisy, sparse galaxy catalogs with greater accuracy than traditional algorithms. Convolutional neural networks can characterize the properties of voids, their profiles, their shapes, their environments from two-dimensional projected images of the galaxy distribution with high efficiency. These methods are still in development, and their systematic properties, particularly the extent to which they can generalize from training data to real observations, require careful validation. But they represent a direction of methodological development that may substantially increase the scientific return from future large-scale structure surveys. The connection between voids and modifications to general relativity is worth elaborating in more detail. General relativity predicts a specific relationship between the gravitational potential, the matter density, and the geometry of spacetime. This relationship, described by Einstein's field equations, has been tested with exquisite precision in the solar system through the precession of Mercury's orbit, the deflection of light by the sun, gravitational time dilation, gravitational redshift, and the timing of pulsar signals in binary systems. In every case, general relativity's predictions have been confirmed, but these solar system tests operate at length scales of roughly 100 astronomical units, the size of the solar system, and gravitational field strengths characteristic of normal stars and planetary bodies. The scales relevant to the cosmic web, hundreds of millions of light years, and the gravitational field strengths characteristic of large-scale structure, much weaker than solar system fields, are a completely different regime. There are theoretical motivations for testing gravity on cosmological scales. Several proposals for explaining dark energy involve modifications to general relativity rather than a cosmological constant. In these theories, the apparent acceleration of the universe's expansion is not due to an energy component with negative pressure, but to a modification of the gravitational force law on large scales. These theories make different predictions for the growth rate of structure compared to general relativity with a cosmological constant. The growth rate is precisely what void outflow measurements constrain. By measuring how fast galaxies are evacuating voids on large scales, cosmologists directly probe the growth rate of density perturbations. If this growth rate differs from the prediction of general relativity, it could indicate modified gravity. Current void outflow measurements from existing surveys are broadly consistent with general relativity, but they are not yet precise enough to rule out modest deviations. Future surveys with their larger void catalogs and more precise velocity measurements will tighten these constraints substantially. FR gravity, Dvali-Gabadadze-Paradi gravity, and Galilean gravity are among the modified gravity theories that have been most extensively tested using large-scale structure observations. Each of these theories predicts a different screening mechanism, a way in which the modification to gravity is suppressed in dense environments so as not to conflict with solar system tests while remaining active in underdense environments. Voids, being the most underdense environments in the universe, are precisely where the modifications would be least screened and most detectable. The Boytes void, with its extraordinary underdensity, would in some modified gravity theories exhibit significantly different dynamics compared to the predictions of general relativity. The outflow velocity of the 60 galaxies within the void, and of any additional matter at the void boundaries, would differ from general relativistic predictions if gravity is modified. While measuring these outflows precisely for the specific case of the Boytes void is observationally challenging at its distance, the method is well established for statistical samples of smaller voids in nearer survey volumes. The diversity of scientific applications of cosmic void science, from dark energy to modified gravity, from neutrino masses to galaxy evolution, from the integrated Sachs-Wolf effect to the kinematic Sunyaev-Zeldovich effect, from topological methods to machine learning, reflects how central the study of large-scale emptiness has become to 21st century cosmology. The Boytes void stands at the extreme end of this scientific landscape, the largest known expression of the cosmic void phenomenon, a physical structure that challenges our understanding of structure formation and tests the limits of cosmological models. Its investigation, over the decades since its discovery, has been part of the transformation of void science from an astronomical curiosity to a fundamental cosmological probe. What we know with confidence is this: the universe is mostly empty. Its matter is organized in a filamentary web, gravity sculpted over billions of years from quantum fluctuations laid down in the universe's first moments. The largest known hole in that web, the Boytes void, sits 700 million light-years away, spanning 330 million light-years, containing almost nothing. What we are still learning is how precisely the standard cosmological model predicts the existence of such a structure, what the void's properties tell us about dark energy and modified gravity, what the galaxies within it reveal about evolution in extreme environments, and what its ultimate fate will be in a universe driven toward infinite expansion by dark energy. These questions are being actively pursued. The answers, when they come, will deepen our understanding of the universe we inhabit, a universe that is, at its largest scales, characterized not by the brilliant structures we see in photographs of galaxies and nebulae, but by the vast, cold, nearly featureless emptiness between them. The Buddha's void is that emptiness at its most extreme.